Welcome to Module 2. In this module, we're going to shift the way we think about waste. Agriculture doesn't just produce food, it also creates leftovers like crop residues, manure, and byproducts from processing. Traditionally, these have been seen as a burden. But with science, technology, and creativity, they can become valuable resources, sources of energy, fertilizer, even new products. As we go through this unit, I want you to ask yourself, if waste isn't really waste, but a resource, how can we design systems that capture its value? By the end, you'll see how turning waste into resources helps the environment, the economy, and communities, and you'll be challenged to think about what waste in your own life could be transformed into instead of thrown away. Here's what you'll be able to do by the end of Module 2. This module has 3 lessons, each with a different focus. First, you'll learn the 5 main pathways for handling food waste: landfill, composting, bokashi and anaerobic digestion, biochar and insect bioconversion, and compare their greenhouse gas impacts. Then we'll dive into something called carbon math, which helps us put numbers on the emissions avoided or produced by each method, so we can make real evidence-based comparisons. Finally, you'll learn how to measure waste and calculate its carbon footprint, applying those skills to school or community settings. By the end, you'll not only understand the science, but also be able to recommend solutions for real-world waste problems, balancing climate, economics, and practicality. Let's start with the big question. What if waste is actually a resource? Right now, food waste is often just thrown away. But not all disposal methods are equal when it comes to the climate. Think about 5 possible pathways: landfill, aerobic composting, anaerobic fermentation like bokashi, biochar production, and insect bioconversion. Each has different processes, outputs, and greenhouse gas impacts. For example, landfill generates methane, a very potent greenhouse gas, while biochar locks carbon into soil for centuries. Before we go further, I want you to predict which of these do you think is best for the climate, and why might the most climate-friendly option not always be the one most used in real life? Let's make this real. Imagine an orange peel. Where does it go once you throw it away? It could end up in a landfill, in a compost pile, in a bokashi bucket, in a digester, in a biochar kiln, or even in an insect farm. Each choice has a very different outcome, not just for emissions, but also for nutrient recovery. Organic waste isn't just trash. It's carbon, nitrogen, and minerals. The question is whether those nutrients get lost in a landfill or recycled back into our soils. So every pathway is really a decision point. Does this peel become a problem? Or does it become part of the solution? Now, here's the key idea. Organic waste is full of value. It contains carbon, nitrogen, phosphorus, and minerals, things plants need to grow. If it goes to landfill, those nutrients are wasted. But if we recycle it, those same nutrients can boost soil fertility, support crops, or generate energy. This is where circular thinking comes in. Waste can either contribute to climate change, or it can help us fight it. I want you to pause and think. What are some ways food waste could be used to help the environment instead of harm it? Compost, bioenergy, fertilizers, animal feed. There are lots of possibilities. The main takeaway is this: waste is not just trash. It's a choice, and the pathway determines whether it harms or helps. Here's the contrast. In the US, food waste is the single largest component of landfills by weight, about 21%. When food rots in landfills, it doesn't decompose with oxygen. Instead, it breaks down anaerobically, releasing methane. And methane is more than 25 times as powerful as carbon dioxide at trapping heat. So, when we landfill waste, we're not just losing nutrients, we're adding to climate change. Nutrient cycling offers the opposite outcome. Instead of trapping carbon underground and releasing methane, it returns nutrients to soil, supports plant growth, and reduces emissions. A simple way to frame this is: landfill equals no, nutrient cycling equals yes. The choice is really that stark. Let's look at the scale of the problem. About 40 to 50% of all food produced in the US is never eaten, almost half. And most of that waste happens in homes and restaurants. This waste is responsible for nearly 9% of US greenhouse gas emissions, from the farm inputs used to grow the food all the way to landfill methane. In landfills, food waste fills about 21% of total space, making it the single largest category by weight. And remember, when we waste food, we are also wasting the water, land, energy, and labor that went into producing it. To picture it another way, imagine buying 2 bags of groceries and throwing one straight into the trash. That's basically what we're doing at the national level. So the stakes are high. Cutting food waste is one of the biggest climate opportunities we have. Before we dive into the pathways, let's pause and think about systems. A linear system is the kind we're used to take, make, use, and throw away. Food and resources flow in one direction, and waste piles up at the end. A circular system is different. It keeps materials cycling back into use. Waste is minimized, nutrients and energy are recovered, and the system regenerates itself. We often summarize this with the 5 R's: refuse, reduce, reuse, repair, and recycle. Keep this in mind as we compare waste pathways. Some are more linear, while others are more circular. Here's a video to illustrate the difference between linear and circular systems. As you watch, look for moments where waste is diverted back into use. Those are the points where a circular economy is being created. After the video, you'll be asked to share one example you saw of a circular solution in action. Now, let's get specific. Pathway 1 is the landfill, and it's the most common in the US. When food waste is buried in a landfill, there's no oxygen. That means microbes break it down anaerobically, producing methane. And methane is 28 to 36 times stronger than carbon dioxide at trapping heat in the atmosphere over 100 years. To put it into perspective, just 1 ton of food waste can generate up to 3/4 of a ton of CO2 equivalent methane. On top of that, all the nutrients in the food, carbon, nitrogen, phosphorus, are lost, trapped away instead of going back to soil. When you toss a banana peel in the trash, it doesn't disappear. It sticks around, contributing to climate change. Pathway 2 is aerobic composting. This process is oxygen-rich, so microbes break food down aerobically, producing carbon dioxide instead of methane. The climate impact is much smaller. Emissions are up to 90% lower compared to landfilling. Composting also has the advantage of nutrient cycling. The finished compost returns nitrogen, phosphorus, and carbon back to the soil, improving fertility and structure. In 4 to 6 weeks, you get a crumbly, earthy-smelling material teeming with beneficial microbes. Composting is a circular process, taking what would have been waste and turning it back into something plants can use. Why does composting produce less methane than landfills? Because oxygen changes the entire microbial community. Now let's look at bokashi fermentation. Bokashi is an anaerobic process, but unlike landfills, it doesn't let food rot. It ferments it. Think of it like pickling your food scraps. In a sealed container, you layer waste with inoculated bran full of beneficial microbes. In about 2 weeks, the microbes ferment the waste into a nutrient-dense mash. This method works especially well for foods that are difficult to compost, like citrus, meat, dairy, or cooked food. And because it's sealed and controlled, it produces almost no odor. The result isn't finished compost, but a fermented substrate that enriches soil once it's buried or added to a compost pile. Bokashi has several unique strengths. First, it's versatile. You can include foods that normally cause problems in compost. Second, emissions are very low. There's virtually no methane or carbon dioxide released during fermentation. Third, the byproducts are valuable. The bokashi tea, or liquid runoff, can be diluted and used as fertilizer, and the fermented mash enriches soil when buried. It's a small-scale, low-tech solution with surprisingly big benefits. Imagine a classroom or cafeteria using bokashi buckets instead of sending scraps to the dumpster. Of course, bokashi isn't perfect. It requires airtight containers, consistent additions of bran, and attention to detail. If the container isn't sealed properly, the fermentation fails. And remember, the mash isn't ready to use right away. It still needs to be buried in soil or added to a compost pile for microbes to finish the decomposition process. So, while bokashi is flexible and climate-friendly, it also demands careful management. If you were trying this at home, what challenges might you face? On a larger scale, we have anaerobic digesters. These sealed systems take in manure, food waste, and other organics and break them down without oxygen. The process produces 2 major outputs: biogas and digestate. The biogas can be converted into electricity, heat, vehicle fuel, or renewable natural gas. The digestate can be used as fertilizer, animal bedding, or even horticultural products like soil amendments. Digesters reduce emissions by preventing uncontrolled methane release and by displacing fossil fuel use with renewable energy. Think about it this way. Landfill methane is wasted energy, but digesters capture that methane and put it to work. Pathway 4 is biochar pyrolysis. In this process, dried biomass is heated in low oxygen conditions. Instead of decomposing, the carbon is locked into a solid form, biochar. This stable carbon can persist in soil for centuries, effectively storing carbon and preventing emissions. Biochar also improves soil by holding water and nutrients and providing a habitat for microbes. You can think of biochar as little charcoal sponges in the soil. It's one of the most climate-friendly pathways because it actively removes carbon from the short-term cycle and puts it into long-term storage. Biochar has three big benefits. First, it acts as a carbon vault, locking up to half of the carbon and waste for centuries. Second, it's a soil super sponge, retaining water and nutrients, reducing fertilizer runoff, and improving yields. Third, it's a microbe mansion, creating homes for beneficial soil organisms. So biochar is a win-win. It helps combat climate change and builds healthier soils. Which of these benefits do you find most surprising? The climate impact, the soil impact, or the microbial support? Of course, biochar also has trade-offs. Pyrolysis requires very high heat, which means significant energy input. Kilns can be expensive to build and operate. However, the process produces syngas, a type of gas that can fuel the kiln itself, reducing outside energy needs. The key is having a reliable stream of biomass, like yard waste or crop residues, to feed the system. This is where circular thinking comes in. Sometimes you need to invest energy and resources up front to get much larger climate and soil benefits in the long run. If you were a farmer, what would you take under consideration when deciding whether biochar was worth the investment? Our final pathway is insect bioconversion. Here, black soldier fly larvae are the stars of the show. These insects can eat enormous amounts of organic waste, everything from food scraps to agricultural byproducts. As they feed, they reduce the volume of waste by as much as 80%. Then, the larvae themselves become a valuable product. They're high in protein and fat, making them excellent animal feed. The byproduct left behind, called fraст, is a nutrient-rich fertilizer. So this method does two things at once. It diverts food waste from landfills and creates two new resources, feed and fertilizer. It's a great example of nature helping us solve a human problem. Now that we've seen the 5 main pathways, let's zoom out to a bigger concept. Valorization. Valorization means creating value from waste. Double valorization means taking it a step further, using the byproducts from one process to create even more products. For example, you might ferment food scraps into bokashi, then use those fermented scraps to feed insects, creating protein and fertilizer. Or you might compost, and then use the residuals for bioenergy. This way, we squeeze the maximum benefit out of each ton of waste. It's about asking, how many useful products can we generate from something people usually throw away? There are real-world examples of this creativity in action. Farmers can grow oyster mushrooms on crop residues, then compost the leftovers. Used cooking oil can be collected and turned into biodiesel for buses. Fruit pulp from juice production can become biodegradable plastics. Manure plus food waste can even be used to grow algae, which is then pelletized as fertilizer. Notice how in each case, something considered waste becomes the input for something valuable. This is the mindset shift we are aiming for in circular systems. Every output has a next use. Let's pause and summarize what we've learned. Here are the 5 main pathways at a glance: landfill, composting, bokashi and anaerobic digestion, biochar, and insect bioconversion. For each one, think about the inputs it can handle, the process it uses, the outputs it creates, and the climate impact, whether it emits greenhouse gases or avoids them. This chart is a cheat sheet that you can keep in mind as we go through the rest of the module. As you look at it, ask yourself, which pathways seem most practical for your school or community? Which ones seem more futuristic or technical? To make smart choices, we need to compare across multiple criteria, not just emissions. Here's the toolkit comparison: energy input, cost and complexity, processing time, main benefits, and key limitations. Some pathways, like composting, are low cost and simple but slower. Others, like digesters, are expensive and complex but give you energy as well as fertilizer. Biochar locks carbon for centuries but requires a kiln and high heat. Insects can reduce waste volume quickly and produce feed, but you have to manage live organisms. This comparison helps us see that there isn't one perfect solution. The best choice depends on your context, your goals, and the resources available. So, what happens to our orange peel? We've seen that the answer depends entirely on the pathway. In a landfill, it becomes methane and wasted nutrients. In compost, it becomes fertilizer and avoids most emissions. In bokashi or a digester, It's transformed into a nutrient-rich product with very low emissions. In biochar, it's locked away as stable carbon for centuries. And in insects, it becomes protein for animals and fertilizer for soil. No single pathway is perfect, but each has strengths. Often, the smartest systems combine multiple methods, compost plus bokashi or insects plus digesters, so that nothing goes to waste. The key message is, waste is a choice. And the choice of pathway determines whether that waste harms the climate or helps the food system. Let's see what this looks like in real life. In California, citrus nurseries had a big waste problem, tons of prunings and residues piling up. Instead of sending them to landfill, researchers designed a circular system. They used bokashi fermentation to turn the waste into nutrient-rich inputs for trees, and biochar to improve soil water retention and lock away carbon. The results were healthier trees, less waste, and fewer emissions. This case shows that circular thinking isn't just theory, it works in practice, and it benefits both farmers and the environment. Before we move into the next section, let's check in with some review questions. First, can you list the 5 major waste valorization pathways we've discussed? Remember, landfill, composting, bokashi, anaerobic digestion, and biochar. Second, which pathway avoids the most CO2 equivalent emissions per kilogram of food waste and why? Here's a hint. Think about which one locks carbon away for centuries. And finally, imagine you have to process food scraps quickly with very little equipment. Which pathway would you recommend? And what trade-offs would you have to accept? Take a moment to jot down your answers, then we'll walk through them together. Here are the answers. The 5 pathways are landfill, composting, bokashi and anaerobic digestion, biochar, and insect bioconversion. Of these, biochar avoids the most emissions, around minus 450 grams of CO2 equivalent per kilogram of food waste, because it locks carbon into a stable form that stays in soil for centuries, and it can even displace fossil fuel use. For the fast and simple option, bokashi is usually best. It works in about 2 weeks, requires only a sealed container and bran, and can handle a wide range of food scraps. The trade-offs? You need airtight containers, consistent additions of bran, and you still need a post-processing step like burying the mash or mixing it into compost. So each pathway has strengths, and the right choice depends on your situation. As we move into Lesson B, the focus shifts to carbon math. The big question is, how do we actually quantify the climate impact of each waste pathway? Each method has different emissions, costs, and outputs. To compare them, we need a consistent measurement system, CO2 equivalent, that shows us not just emissions but avoided emissions too. Each pathway has its own logic. Composting works because microbes use oxygen, so methane doesn't form. Bokashi works because fermentation locks nutrients into organic acids. Anaerobic digesters work by capturing the biogas and turning it into energy instead of letting it escape. Biochar works because it stabilizes carbon for centuries. Understanding why each path works helps us compare them fairly. Of course, none of these are perfect. Composting takes time and space. Bokashi requires airtight containers and a second step. Digesters are costly and need steady feedstock. Biochar requires high heat and equipment. Insect bioconversion needs live larvae and good management. The point is, every system has trade-offs, and that's why context matters. When we compare these methods, we're not just asking which is best, we're asking, best for who, where, and under what conditions? A school might choose bokashi for simplicity. A city might invest in digesters for energy recovery. A farmer might use biochar for soil health. The right fit depends on balancing carbon savings with cost, practicality, and benefits. Looking at carbon math, not all reductions are equal. Composting cuts emissions by about 80% compared to landfill. Bokashi and insect bioconversion go further. Biochar has the biggest climate impact, turning waste into a long-term carbon vault. But again, high impact doesn't always mean easiest to implement. To compare pathways, we use a common unit, delta CO2 eq. That means the change in emissions compared to landfill. Positive numbers mean more emissions. Negative numbers mean avoided emissions. This lets us line up methods side by side and see which ones actually improve the climate picture. Here's how it works. If landfill is plus 500 grams CO2 eq per kilogram and composting is minus 100, then shifting 1 kilogram of waste saves 600 grams CO2 eq. That's the power of delta CO2 eq. It quantifies the benefit of switching from one pathway to another. Let's try it together. Suppose the cafeteria generates 50 kilograms of food waste per day. At landfill rates, that's 25 kilograms of CO2 daily. At composting rates, it's minus 5 kilograms daily. That's a swing of 30 kilograms per day. Multiply by weeks and months, and small shifts make a massive difference. We can also calculate for bokashi or biochar. Bokashi at minus 200 grams per kilogram means 10 kilograms avoided per day. Biochar at minus 450 grams per kilogram means 22.5 kilograms avoided per day. You can see clearly that biochar has the biggest potential. But all three are big improvements over landfill. Now picture this. We map waste across campus. The cafeteria is the biggest hotspot. If all of that waste goes to landfill, emissions soar. But if we reroute it through bokashi, insect bioconversion, or biochar, the numbers change dramatically. Data shows us where interventions make the biggest impact. In one pilot, students diverted cafeteria scraps into bokashi bins. The fermented mash was used in a campus garden, boosting soil fertility and cutting fertilizer costs. At the same time, they measured avoided CO2 compared to landfill. The result: stronger plants, lower emissions, and a visible example of circular economy in action. Time for a check-in. Question 1. What does a negative delta CO2 value mean when comparing waste pathways? Question 2. Order these from most to least climate-friendly. Landfill, biochar, insect bioconversion, compost, and bokashi. And question 3. Digesters cost more upfront but produce renewable energy. When might that be the smartest choice? Here are the answers. A negative delta CO2 means the pathway avoids more emissions than it produces. A net climate benefit. Ranked most to least climate friendly. Biochar, insect bioconversion, bokashi, compost, and landfill. And digesters? They're best when you have steady waste streams, long-term energy needs, and the ability to recoup costs through renewable energy and co-products. That's how carbon math guides smarter decisions. As we wrap up Lesson B and move into Lesson C, I want you to think bigger. We've compared each pathway on its own: landfill, compost, bokashi, digestion, biochar, and insects. But in reality, no single method handles every type of waste perfectly. A school, a farm, or a city will often need to combine approaches. For example, compost might handle yard waste, bokashi might handle cooked food, and biochar might manage prunings or shells. Together, these create a closed-loop system where nothing goes to waste. So the guiding question is, how can implementing multiple waste valorization methods together make a campus or community more sustainable? Keep that in mind as we move into the math and measurement part. When it comes to solving waste problems, it's not enough to say, let's do something. We need to know exactly what's happening. That means asking, where is the waste coming from? How much is being produced? What kind is it? Without this information, we risk putting effort into solutions that don't really make a difference. Measuring waste is like diagnosing a patient. You wouldn't prescribe medicine without knowing the illness. The same goes for waste management. We need data before we can design smart systems. So today, we're going to learn how to measure waste and then connect those measurements to CO2 equivalent impacts. This is the math that makes sustainability measurable and real. The first step is figuring out how much waste you actually have. We don't need perfection. We need enough accuracy to make smart choices. One way is visual estimation. Compare your waste to something familiar, like a standard trash bin or a milk crate. Another way is to count how many bins are filled over a week. That gives you a volume estimate without touching the waste. For more precision, you can weigh one bin to get an average, then apply that across all bins. Even the frequency of emptying bins is data. If they're empty daily, you know the waste load is high. If weekly, it's lower. Let's try a quick thought experiment. Picture your cafeteria's trash bins. How many do you think are filled every day? That's the start of volume estimation. Volume tells us how much space waste takes up, but most solutions require knowing mass, how heavy it is. Why? Because disposal costs, hauling limits, and composting capacity are calculated by weight. The bridge between volume and mass is density. If we know food waste averages about 0.4 kilograms per liter, and a bin holds 50 liters, then mass would be 50 multiplied by 0.4, that is 20 kilograms. That's one bin's worth. To make this practical, we often just weigh one sample bin, and then apply that average to all the bins. Let me ask you, Which would weigh more? A bin of dry leaves or a bin of wet pasta? Exactly. That's density in action. Once we know the mass of a single bin, we can scale up. If one bin is 20 kilograms and it's emptied 3 times a week, that's 60 kilograms per week. That weekly number is incredibly useful. It shows us trends, helps set reduction goals, and allows us to compare strategies over time. Imagine two cafeterias. One generates 60 kilograms per week, another generates 200 kilograms. Where would you focus first if you wanted to reduce emissions? Right? The bigger hotspot. This is where math helps us target action. Finally, we connect waste to climate impact. Not all waste has the same footprint. Food scraps, paper, and yard waste decompose differently and release different amounts of greenhouse gases. That's why we use CO2 equivalent, or CO2e, as a standard unit to compare everything. The formula is simple. CO2e equals mass multiplied by emission factor. For example, food waste has an emission factor of 1.9 kilograms CO2e per kilogram. So 50 kilograms of food waste equals 95 kilograms of CO2e. That's the same as driving about 240 miles in a car. This calculation helps us see how even small changes in waste management can lead to big climate benefits. And once we know the numbers, we can decide, where should we focus to make the biggest impact? Let's ground all of our measurement skills in a real story. Meet Juan and Katie, who share a small dorm kitchen. Like most students, they cook some meals, save leftovers, and toss scraps. Today we'll use their kitchen as a mini lab. We'll measure their food waste, see how quickly it adds up, and connect it to CO2 equivalent so we can talk about climate impact with numbers, not guesses. Before we jump into the math, picture the bin in their kitchenette. What fills it in a typical week? Wilted greens, coffee grounds, or leftover rice? Hold that mental picture. In a moment, you'll estimate the weekly amount. Then we'll scale it to a year and translate it into emissions. This case links directly to what we covered on landfill methane and avoided emissions. Now we'll quantify it for one ordinary kitchen. Let's work the numbers together and show our steps so everyone can follow. If the bin is 25 liters and we use a typical density for mixed food scraps of 0.4 kilograms per liter, that comes out to about 10 kilograms per full bin. Since Juan and Katie empty that bin twice per week, that adds up to roughly 20 kilograms of food waste each week. Using a food waste emission factor of 1.9 kilograms of CO2 equivalent per kilogram of waste, that translates into about 38 kilograms of CO2e every week if their scraps were landfilled. Over the course of a year, multiplying by 52 weeks, this amounts to nearly 1,976 kilograms of CO2e, almost 2 tons. That's the climate footprint of just one small dorm kitchen bin. As we calculate, be sure to double-check units as we convert liters into kilograms and weeks into years, and compare your results with your partner. Notice how these simple measurements, bin size and emptying frequency, quickly become a clear picture of both waste mass and emissions. Now, let's make the numbers mean something. A weekly 20 kilograms of scraps equals about 38 kilograms CO2e per week. Across a year, that's around 1,976 kilograms CO2e, which is around 2 tons. To visualize it, that's like driving a car about 5,000 miles. The takeaway is not shame the dorm kitchen. It's that even small, everyday bins add up to a significant footprint. This is why measurement matters. When we see the scale, we can design better solutions. So, what could reduce that number most quickly in a dorm? Composting, bokashi buckets, insect bioconversion? Jot one idea you'd try first and one constraint you'd have to manage, such as space, smell, time, or buy-in. Quick debrief before we close. Which location on campus likely produces the highest CO2e from food waste? And how do you know? Think in terms of measurement data multiplied by emission factors. If we put insect bioconversion at that hotspot, what happens to CO2e? And what co-products do we make? Finally, why might a mix of waste valorization pathways beat any single method for a whole campus? Talk it through with a partner, anchor your answers in data, and be ready to share one sentence for each. Let's chat. The cafeteria or dining hall is usually the top emitter because it generates the largest mass of scraps daily. And we know this from bin counts and weights combined with emission factors. Insect bioconversion would lower CO2e significantly, around minus 300 grams of CO2e per kilogram avoided, and at the same time it would produce two valuable co-products. Larvae, which can be used as animal feed to replace soy or fish meal, and frass, which is a nutrient-rich fertilizer. Using multiple waste valorization methods is better than relying on a single one because different wastes are best suited to different systems. A mix maximizes resource recovery, minimizes emissions, and adds resilience when one pathway reaches its limit. That's how measurement and carbon math guide smarter designs, by allowing us to target hotspots, choose the right tools, and prove the impact. As we wrap up Module 2, let's take a step back and look at the big picture. We started by asking how food waste could be redefined as a resource, and we explored 5 different pathways: landfill, composting, bokashi, anaerobic digestion, and biochar, each with unique benefits and trade-offs. We also practiced doing the carbon math, learning how to compare emissions across systems and identify which pathways deliver the biggest climate benefits. Then, we moved into measurement, seeing how simple tools like bin counts and density estimates can generate powerful data for planning solutions. The key takeaway here is that waste isn't just something to throw away. It's a material flow that can either worsen climate change or help us build circular systems. By using systems thinking, we can see how waste connects to carbon, soil health, energy, and even economic opportunities. And we can design smarter strategies that close loops instead of breaking them. Before we move forward, let's visualize how everything we've learned in this module connects. Imagine a mind map that links the 5 waste valorization pathways, the carbon math that measures their impact, and the tools we use to track waste in real-world settings. At the center is organic waste, and branching from it are the strategies that transform it. Compost brings nutrients back to soil, bokashi and digesters recycle food into fertilizer and energy, biochar locks carbon away while improving soil, and insect bioconversion creates both feed and fertilizer. Around the edges, you see the supporting ideas we've practiced: data collection, CO2 equivalent calculations, trade-off analysis, and systems thinking. This mind map is your toolkit. It shows how different approaches don't stand alone, but interlock to form a circular economy. Keep this structure in mind as we move forward, because the skills you built here will connect to water, energy, and farming systems more broadly. Now let's shift to thinking about your future. The knowledge and skills from this module don't just live in the classroom. They connect to real career paths in sustainability, agriculture, science, and engineering. If you're interested in policy, you might work on designing food waste reduction programs or advising governments on climate-smart agriculture. If you lean towards science and technology, you could become a researcher in composting microbes, a biochar systems engineer, or a data analyst mapping carbon footprints. Innovation and business offer other opportunities: developing circular food companies, upcycling products, or working on sustainable packaging. And of course, careers in farming, urban agriculture, or nonprofit advocacy all benefit from understanding waste to resource strategies. As you consider these pathways, think about how your own strengths, whether in science, communication, design, or leadership, might fit into building a more circular food system. To close, here's a preview of what's coming next. In our upcoming sessions, you'll have a chance to apply these ideas through hands-on activities that bring waste to resource strategies to life. You might measure and sort actual cafeteria waste, calculate the CO2 equivalent of your school scraps, or design small-scale pilots using compost bins, bokashi buckets, or even insect larvae systems. You'll also practice presenting solutions, just like a real sustainability consultant would do for a school or city. The point of these activities is not just to test your knowledge, but to give you the confidence to turn ideas into action. When you leave this module, you'll be ready to look at waste differently, not as a problem to hide, but as a resource you can measure, calculate, and transform. That mindset shift is the first step toward becoming a leader in building sustainable food systems.